our absolute temperature scale, and Celsius is just a relative temperature scale, right? The 0 is set by the freezing temperature of water, but things can actually get a lot colder than that, right? And so if you're at 0 degrees Celsius, you can still have gases at that temperature. But if you were to plug them into this equation, it would make no physical sense because you're dividing by 0, right? So that's mathematically not allowed. So use the absolute temperature scale for which there is no realistic 0 to ever reach. It can be very, very small, but not 0. So that's why we always go to Kelvin in these types of calculations. All right, so how do we isolate, or what was our two temperatures that we ended up using for this? Once you converted the Celsius to Kelvin, what were the two temperatures? It was 4.0 ATM over 298.15 Kelvin, P2, and we'll add 673.2 or 15 Kelvin. All right, so these are our two temperatures. All right, and so we're always making sure to keep our units in the calculation. I'll try and make sure I'm writing only higher so you guys can see it in the back. And so we have to isolate P2 to solve for our new pressure. So how do we do that? You have to multiply both sides by 673, right? So this would then become 673.15 Kelvin over 298.15 Kelvin times the initial pressure, which was 4 atmosphere, equals our second pressure, right? What happens to our units of Kelvin? They cancel out, right? Which makes sense because we're left with units of what? Atmospheres, which is what we want because we want a unit of pressure, right? So we plug this into our calculator, we get 673. What number did you guys get?
It ended up being 9.0.
9 point what? 0 atmosphere equals P2, right? Does that make physical sense to us?
Yes.
Why? Yeah, because as we heat up the can, we expect the pressure to build up inside, and so the pressure should be larger than what we started with, right? All right, so that makes physical sense. Are there any questions on this problem and Guy-Lussac's law in general? Laura?
Is the atmosphere and the other pressure units thing that's qualified, do they have like conversion factors?
Yeah, there's conversion factors. So if you look at the practice final, for example, you see I put the conversion factors going from bar to atmosphere to millimeters mercury. Those are the common ones that you'll see. I personally, atmospheres is the simplest to work in, but you just have to keep track of whichever one you're using. Where's another question? I saw another hand raised up. Okay, I saw the reflection. That's how I saw it.
If you divide those two and multiply by the 4,
To do this, I multiplied 673.15 to both sides, 673.15 Kelvin to both sides. This cancels out on the right-hand side of this equation. And then these two, I just made the ratio, right? If you multiplying and dividing things, you can do it in any order. It doesn't matter what you do it in. I just did that because it's easy to see the units of Kelvin cancel out when we do that. All right, so for this one, if we're working in units of pressure, as long as we have one unit of pressure for one pressure we're starting at, you don't really have to convert it because the other unit, in this case, the temperature is always going to cancel out in these problems. Where you do have to start being concerned about it is when we're looking at systems where we look at the combined gas law. So the combined gas law is an early derived empirical relationship that just combines everything that we've said before, right? We had Charles' law, which said P1V1 equals P2V2. We had, Boyle's law, P1V1 equals P2V2. We had Charles' law that said the volume over the temperature is V1 over T1 equals V2 over T2. And then we also had Guy-Lussac's law, which was the pressure and temperature are also directly related. So all of those things together, now if we have multiple things changing at the same time, should change the same way, right? So the pressure and the volume both increase as the temperature increases. We wouldn't say, though, that these things are directly related, though, because we have multiple variables. It's not just, X and Y, it's X, Y, and Z. It's a little bit more complicated to think about those things intuitively like that. One way you can also think about this is just a side note, a pressure times a volume, these dimensions are equal to dimensions of energy, right? So we can say that as we increase the temperature, the energy also has to increase. And that should make some intuitive sense, right? The energy is related to how fast these molecules are moving. As the temperature goes up, the molecules move faster, their energy should increase, right? So we could say that the energy and temperature are directly related. But this doesn't change anything about what we've said before. It's just combining all the laws we've talked to up until this point into one law. All right, and that's why it's called the combined gas law. And so this is for a system where you're changing the pressure, temperature, and the volume of the system. So this is like heating up a stretchy balloon and then putting it under water or something like that, right? Where you increase the pressure by putting it deep in the ocean. And so these, right, these problems are just longer to look at because there is more variables to see, right? So you have a 25 milliliter sample of gas has a pressure of 4 atmospheres and a temperature of 10 degrees, right? Those three things completely define the state of the initial gas, right? Of the gas initially, right? We have the volume, we have a pressure, and we have a temperature. These three things completely define the state of the gas initially. And it's saying, well, what is the volume of the gas after we've done a pressure change and a temperature change, right? So we're given 3 variables and then given another 2 variables for 5 total. And we have 6 that are related to each other by the combined gas law. And so then we just perform our algebra to solve for the final volume in this case, right? So we know what we're solving for because the problem is asking for what is the volume of the gas after all of these changes. So we start by writing our equation, P1V1 over T1, P2V2 over T2. I'll highlight the values that we know. We're given all of the initial values, right? And then we're given the final pressure and the final temperature. And what do we have to do with the temperature here? Yep, temperature converts to Kelvin. We're in Celsius, degrees Celsius right here. Oh, I already converted it over there. But in the problem, it gives it to you in Celsius, right? So we have to convert this, right, into Kelvin, right? So that's what those values are in Kelvin. And then after that, it's just algebra, right? So we want to solve for what again? What are we solving for? I'll highlight in red. V2, right? We want to solve for V2, right? So we're solving for this. So before we plug in numbers, let's go through just some practice with some algebra. How do we isolate V2 here? We're going to have to do some multiplication and some division, right? Right, what are we going to multiply by? T2. Multiply T2 to both sides. And what are we going to divide by? P2, right? Divide P2 to both sides, right? And so when we do that, I'm going to put that on the next page just so I don't run out of room, and I know some of you guys are looking kind of low here. So I'll give you guys a second to finish writing that before I start writing. Okay. So when I do that, I have P1V1 over T1 equals P2V2 over T2. Multiply by T2 to both sides. And divide by P2 to both sides, right? On the right-hand side of this equation, everything will cancel out. And on the left side, we have our new expression. We have V2 is equal to T2 P1 V1 over P2 and T1, right? And we see what happens to what's going to happen to our units of pressure here. cancel out. We can see that because we have 2 units of pressure right here. And what about our units of temperature? Temperature will also cancel out because we have 2 quantities of temperature divided by each other. So we're left with units of volume because that's the unit, and that makes sense because we want the units to be volume. And so let's look back again. So is it going to be immediately obvious what the change in volume will be? Well, we see that the volume starts at 25 milliliters. We start from a pressure at 4 atmospheres and go to a pressure of 1 atmosphere, right? So the pressure in temperature, or sorry, the pressure in the volume, if we increase the pressure, what should happen to the volume? From our initial Charles law. How are pressure and volume related? It should decrease, right? Because as we compress things, we're adding pressure. The volume is getting smaller, right? The volume is getting smaller. So we see that we're going from a larger pressure to a smaller pressure. So in this case, the volume is increasing, right? We're going to a smaller pressure, so the volume, pressure's going down, volume should go up. All right, what about from the temperature? We're starting at a temperature of 10 degrees and going to 18 degrees, right? So the temperature, are we increasing or decreasing the temperature? We're increasing it, right? So in how are temperature and volume related? They're directly proportional to each other, right? So if the temperature goes up, what happens to the volume? That goes up as well. So both of them should increase the volume. So we should see an overall increase in the volume. We can tell what's going to happen based off of these 2 changes. All right, we can use a little bit of our intuition to guess, or not guess, or estimate what we expect to happen. So our answer should make sense for that. So I'm going to plug in all the values now. We get our temperature of 18 degrees, which was 291 Kelvin. Oops. 291 Kelvin times our initial pressure, which was 4 atmospheres, times our initial volume, which is 25 milliliters. And our final volume should be larger or smaller than 25 milliliters? Larger, right? And then our final pressure is 1 atmosphere, and our initial temperature was 283 Kelvin. All right, we check our units, so this is all going to equal V2. Kelvin cancels out with Kelvin. Atmosphere cancels out with atmosphere, and we're only left with units of milliliter, which is volume, which is what we want. And if I take a look, the ratio 4:1 for the pressures is larger than 1, and the ratio 291 to 283 is also larger than 1. So this will give me a larger volume. I can tell without plugging it into my calculator, just looking at the numbers that are there. Okay, so I have 291 times 4 times 25 divided by 1 divided by 283. And I get that my final volume is 103 milliliters. Right, so these problems are identical to the ones we've done before. It's just more variables, right? So we just added a little bit more variables to the system. Yeah.
Is it with gases for the weight, it's only volume, or is there mass as well?
So there is an amount, and it's related not to necessarily the mass of the gas. It's related to the number of moles of the gas, right? Because when we assume things are ideal, we don't only assume that they don't interact with each other. We assume that the gases occupy 0 volume. Yeah, we'll get to that when we get to the ideal gas law. We'll talk in Avogadro's law in a second. We'll talk about that. How is that proportional to the number of moles of the gas? But when we assume things are ideal, we assume not only do they not interact with each other, we assume that they don't have any volume. We assume that they're just point particles, and because they're just point particles, it doesn't matter if it's helium or methane gas, right? Those are, in real life, those are very different sized gas molecules, but in ideal gases, we assume they're the same.
So there's no like grams of X gas?
You can have grams, but you convert it into moles when you're calculating the ideal gas law, right? Or when you're dealing with the moles of gas in your system, right? So if you're given grams, that is a way of looking at amounts, but usually when you're adding different moles of gas, we're going to learn that they add up to the total pressure of whatever's there. All of them contribute to the total pressure by adding. So if you have different grams amounts, you have to make sure they're all in moles to get the total pressure of the gas.
So it's not like a property of gas.
Yeah, the amount, so grams in moles are technically related to each other, right? But if we're comparing different gases, they would have different moles based off of the mass, right?
So volume is what we like stick with when measuring it on the device.
Yeah, so the variables that define it are the amount, which is moles, which is technically grams. But the reason that we don't do grams is because different gases have different masses. But it's not the mass that's important for determining the system, it's the moles that are important for determining the system. So it's the amount, the volume, the temperature, and the pressure, and all of those things completely define the state of the gas. Mm-hmm. All right. Any other questions on this problem? Right, so we talked about pressure, temperature, and volume up to this point. So then we have Avogadro's law, right? Avogadro, we love that guy. He has that number we like. He was, also a physicist and worked on how does the volume of a gas or pressure of a gas depend on the number of moles of the gas. And like we said earlier, we stated it, the volume of gas is directly proportional to the amount of gas that is there, right? If the volume goes up and you allow more gas to go into the system, it will pull more gas inside. Where do we see an example of this? Well, if we think about every time we breathe, right, our lungs don't suck in air. What they do is your diaphragm expands, the volume increases, and you increase the number of moles of gas from the atmosphere into your chest, right? You're not isolating the system, right? Your mouth has to be open. You have to allow the airway to be open to allow for more moles of gas to then move into your lungs. If you didn't, then the temperature inside your chest would change and the pressure inside your chest would change, right? That's what the other gas laws say. But we don't do that. We allow air to flow in. So to accommodate that change in volume, we don't change the temperature because the temperature of inside our lungs and outside is roughly the same. And the pressure is roughly the same. We're in equilibrium with the pressure of the atmosphere around us. So how do we accommodate that change? Well, we allow more moles of gas to flow into our lungs, right? And that's how we breathe. That's how we get oxygen to our blood, right? By expanding our diaphragm, volume goes up, number of moles of gas has to go up if the pressure and temperature are staying the same. And so as pressure and temperature stay the same, the volume, initial volume, and the initial number of moles are directly related to the final volume and the final number of moles, right? So what this is saying is if we allow pressure to stay the same, temperature to stay the same, the only way we can accommodate the change in volume is by allowing more gas to flow into the system, right? Otherwise, the pressure wouldn't stay the same, right? It's the same way, when you make a suction cup, you squeeze it, decrease the volume, you put it to a surface, right? It starts pulling, that creates a pressure vacuum, right? It doesn't allow, you've made a tight seal so no moles of gas can accommodate, so it creates a pressure that keeps it sucked to whatever glass that it's on, right? We don't do that with breathing, we allow air, right? As soon as you lift up one of the sides of the suction cup, moles of gas flow in, and then the volume goes back to normal, the suction cup pops off because the pressure is equal now, right? So those are some examples of where we see Avogadro's law. So common example of this is saying the volume and number of moles is directly proportional. Right? And it's the exact same thing. You could have the exact same thing for the pressure too, right? If you have a very rigid container, like a gas canister, you forcefully add more gas to the container, right? The container gets pressurized, right? Like oxygen when you go scuba diving, that's very pressurized gas. So the pressure goes really high inside a scuba tank because you're forcing more moles of gas in there. Right, so this is true for both volume and pressure. And so Avogadro's law Also allows chemists to relate volumes and moles of gas in chemical reactions, right, that you knew it was coming, to the moles that happen in a chemical reaction. So when we're looking at limiting reactant, calculating percent yield, how many products are we going to make, right? That's related not to just the concentrations of the species, the molecular weight, the grams, but also now because we're saying that the pressure of a gas and the moles of the gas are related, that the pressures of the system also affect how many products and how many reactants we're going to use, right? So pressures, all this stuff, talk about chemical reactions, is also related to the pressure of the system, right? So for example, if you want to increase more products happening for a system like this, we have 3 moles of gas on the left, 2 moles of gas on the right. If we increase the pressure of the system, I'm not going to test you guys on this, but the equilibrium shifts the reaction to equalize the pressure, and it's going to go to the side that has less moles of gas. So you can force this reaction to happen just by changing the pressure of the system. Okay? And so you can explain a lot of chemistry, not just through concentrations, grams, molar mass and stuff, but also through the pressures of the gases that are involved for gas-phase reactions. Right? So this is an important, powerful idea for chemistry. And this is still just assuming that these are ideal gases, which isn't even real life, right? Real gases aren't point particles, and they have intermolecular forces, right? But we can get a lot of valuable information just from understanding a model system like these. Okay. All right, so let's look at this example. So we have a helium gas, right? So now we're putting it in terms of the mass of 18 grams occupies 1.6 liters at a particular temperature and pressure, right? So we're saying it has a volume at this temperature and pressure. What mass of oxygen would occupy 1.6 liters at the same temperature and pressure, right? So this is what Laura was asking. Well, the amount, can we relate that to the mass? We can, but this mass of oxygen, right, would be a different, right, amount of oxygen. Why? Because nitrogen and oxygen gas don't weigh the same. So the moles of both are not going to be the same. Right? So we have an initial number of moles, and we have the final and initial volumes. Those are going to be the same. So we have V1 equals V2 equals 1.6 liters. And we're saying if we have 18, right? So this is probably won't give you guys a question exactly like this, is just to highlight an idea. The 18 grams of helium gas, so helium gas is He, it's a monoatomic gas. We have 18 grams of helium gas. So that means to get the number or the mass of oxygen, right, we need the same volume occupied by that helium. Because we're dealing with ideal gases, we don't distinguish between moles of helium and moles of oxygen. Those two things give us the same volume of our system, right? Because we're assuming that a helium atom and an oxygen atom are both point particles that don't interact with each other. Right? We have nothing about the mass of the gas in any of the variables we've talked about. So we convert the helium into moles of helium. And once we convert the moles of helium, we know the same number of moles of oxygen gas will occupy the same space. Why? Because we don't distinguish between moles of different gases, right? 1 mole of oxygen gas, according to an ideal gas, is the same thing as 1 mole of helium gas, right? They're both massless point particles that don't interact with each other. So we just replace the moles of helium with moles of oxygen gas, and then convert that back to grams, right? And this allows us to go to grams of O2. Why? Because we know we're still occupying the same space. If we were to change the volume, then we need to account for a new amount of moles, because the volume and the moles are directly related. But if we're occupying the same volume, it doesn't matter what gas we have there. All moles of gas are equal to each other, regardless of what element it is. So this we would convert 18 grams. And how do we convert grams of helium into moles of helium? All right, we use the molar mass of what? Helium. So what is the molar mass of helium? You want to tell me? 4.003 grams of helium per 1 mole of helium. Then, since 1 mole of helium gas equals 1 mole of oxygen gas, because we don't distinguish between those, our molar ratio is 1 mole helium gas is equal to 1 mole oxygen gas. And then how do we convert moles of oxygen into grams of oxygen? Molar mass of what? Oxygen, right? And that should be 32.00 grams O2, because oxygen is a diatomic gas. Doesn't matter though, because ideal gases, we don't care if they're diatomic, triatomic, polyatomic gases, it doesn't matter. Per 1 mole O2. And so if we plug that all in, we get 18 times 32 divided by 4.003, right? So this is 144 grams of oxygen. All right, so this is why we don't consider the mass of the gas as part of its equation of state, because we don't distinguish between different gas molecules. A 1.6 liter container of helium gas weighs a lot less than a 1.6 liter of oxygen gas, even though both of them contain the same amount of moles, right? They both have the same temperature, they both have the same pressure, they both have the same volume. One just has a different mass from each other because it's the moles of gas that are important for understanding the state of the gas itself. Right? A real gas, they would have little correction terms to the pressure, volume, and temperature. But even if you look at a real gas, they're going to be mostly identical. It isn't until you get to very cold temperatures or very high pressures where you start to see a lot of differences. Why? Because gas molecules tend to be so far apart from each other that they never see each other. All right, so this is how you would go about something like this, or using Avogadro's number explicitly. All right, like I said, I won't give you a problem like this. This is just to illustrate the idea that it's the moles of gas that are important for ideal gas systems. All right, any questions on that? Okay. So just some things to define. Standard temperature and pressure. These are the states and molar volume. These are states that people set aside as the standard state for most things. So if you guys go farther in chemistry, you'll learn about ways to calculate different heats of reactions, entropies, free energies, and all these things. A lot of these things are done at standard temperature and pressure, right? So standard temperature is 0 degrees Celsius, right? So 273 Kelvin. Standard pressure is 1 atmosphere, right? So that's a standard pressure, or 760 millimeters of mercury. The standard molar volume is going to be 22.4 liters. And these are just what we set as our arbitrary standards. So that's why most things are going to be measured there. In terms of standardized tests and things like that, the STP is used a lot because they want to see if you remember what standard temperature and pressure is. So they'll say, this reaction happens at STP, predict the pressure of the products or something like that. And that's just, testing you. Do you remember what the standard temperature and pressure are? So if you see STP, that implies 273 Kelvin, 1 atmosphere, and 22.4 liters, right? All right, so the molar volume, right? 1 mole of any gas. Doesn't matter if it's helium, oxygen, or nitrogen gas here, they all occupy the same volume. Why? Because all are ideal gases. And although it's such a big simplification, again, it's actually pretty powerful. Most of these results hold true for a lot of conditions, right? Ideal gases give us very accurate descriptions of real world gases. And so at this temperature, at this pressure, at this 1 mole quantity, you have a volume of 22.4 liters. All right, so is anyone still writing this? Let's see, do I want to do... All right, I'm not really gonna skip that problem. We're gonna go straight to the ideal gas law. So the ideal gas law is combining all the laws that we've described before, the combined gas law and Avogadro's number. And this gives us what's called the equation of state. This is the equation of state for an ideal gas, right? So if you define the pressure, the volume, the number of moles, the temperature of an ideal gas, you get this equation here. So you guys have probably heard the expression PV equals nRT. That's because this is shown ubiquitously in all intro chemistry courses. So this equation completely defines the state of the gas. And the ideal gas constant here, right, R is equal to the, defined as the ideal gas constant. And it's equal to 8.314 joules per mole Kelvin, or you can convert it into units of liter atmospheres per mole Kelvin. This is just how the pressure and volume change as the number of moles and temperature of a system change, right? So the way that people actually discovered the ideal gas constant is if they change the pressure times the volume of a system and change the number of moles and the temperature, this value always changes to some proportionality constant, right? So if you were to plot the pressure times the volume of any gas against the number of moles and temperature of that gas, the slope of that line would give you the ideal gas constant, right? Like when we did our absorption of cobalt, that's how we determined our molar extinction coefficient, remember in that lab, by looking at the slope of the line. That's how people did this for the ideal gas constant. And the ideal gas constant doesn't just show up for gases. It shows up in thermodynamics for many systems. It shows up in statistical mechanics for many systems. It's a fundamental constant related to another constant that if you go far enough on, you'll learn plenty about, right? So this is the ideal gas law. And it relates the number of moles, temperature, pressure, and volume of any ideal gas. The same assumptions that we've done before we use here. All right, so how would we approach something like this? If we have a sample of gas that has a volume of 8.6 liters at a temperature of 0 degrees Celsius and a pressure of 1.5 atmospheres, how many moles of gas are present? So given any three variables for the ideal gas law, you can determine whatever variable you don't have. All right, so if we use our equation of state, PV equals nRT. Here, this is given in liter atmospheres per mole Kelvin. This value for R here, right? We can change the values or the units of this, and we're asked to solve for N. So before we plug in any values here, how would we isolate N here?
Just divide RT from both sides.
Yeah, we can divide RT to both sides. RT, this cancels out. And we get PV over RT equals N. And what unit should we end up with here? Moles, right? Because N represents the number of moles of the gas. So our pressure is 1.5 atmospheres. We're writing our units down with every step so that we can see them cancel out. Our volume is 8.56 liters. Our ideal gas constant is 0.0821 liter atmospheres per mole Kelvin. And then our temperature is 273 Kelvin. All right, so do our atmospheres cancel out? Yeah, our atmospheres cancel out. We see them cancel out right here. Do liters cancel out? Yep, liters right here cancels out. And what about Kelvin? This Kelvin right here cancels out with the Kelvin in the denominator of the units of our ideal gas constant, which means that our final units are 1 over moles, right? We have 1 over moles. And what's this equivalent to? Just moles, right? Whenever we have a fraction of fractions, we invert the denominator, right? So this is just the same thing as units of moles, right? So our units work out. That's where we want them to be. So then we plug this into our calculator. 1.5 times 8.56 divided by 0.0821 divided by 273. This will give us N equals 0.573 moles of H2 gas. Laura?
How do you get the units for R?
R would be given to you. You won't ever have to. The units for R, as because I know that value is in those units. The units for joules per mole Kelvin is what I have right here, 8.314.
Is that like the same thing?
It's the same constant, just in different units. When you convert a liter atmosphere is a unit of energy. When you convert liter atmospheres to joules, that gives you the...
So this will be given though, right?
Yeah, those values will be given. If you were given different units, then you would just have to make sure the units work out in the problem. But generally, I'm only going to give you the ideal gas constant in these units here.
Not the joules.
Yeah, not the joules and stuff. And it's because an atmosphere is defined as a Pascal, and that's where the conversion factor. It's defined in a unit of pressure that's called Pascal.
That's on the other side of the slide with mercury.
mmHg, bar, Pascal, and atmospheres are the 4 different. Pascals are like the SI unit for pressure, and that's where you get like a 1 over 1,000 in there, because Pascals. We can go through the actual unit conversion.
Only need to know that here is one atmosphere is 760.
Yeah, those would be the only ones yeah. I'm not going to ask you to do things in Pascals. Right, so again, the ideal gas law is the equation of state for an ideal gas. If you know those 4 variables, you can determine everything about that gas. And so the last natural extension of this idea of the gases being so proportional to the number of moles of the gas rather than the mass and the volume and the temperature is something called partial pressures, right? So if we have a mixture of gases, it makes things relatively simple if we treat them ideally. Since the ideal gas particles have no attractions, all right, no attractions, and they all behave as point particles, right? They're not affected by other gas. The total pressure of any system is just the total pressure that's individually given by each gas in the system. Right? So each one, it doesn't feel, if you have hydrogen gas and helium gas exerts its own pressure on the walls. it doesn't feel the hydrogen gas at all. Hydrogen gas also exerts its own pressure on the walls. It doesn't feel the helium gas at all. So the total pressure of this system means you can treat each one separately, and the total pressure is just the sum of all the pressures from each individual gas. Right? And so this is what's called Dalton's law of partial pressure. And it says if you have a mixture of gases, the total pressure is just the pressure associated with each gas. Right? This is because each gas doesn't interact with any other gas. It only exerts a pressure on the walls. That's what it means for it to be an ideal gas.
So like hydroxide.
Hydroxide.
So there's no gases that like mix together.
So you can have actual gas phase reactions, but in terms of understanding the pressure of the system, right, that only depends on the individual addition, right? So these gases are mixed together, but since gas molecules are so far apart, it doesn't really matter that they're mixed together. They don't really interact with each other at all.
Aqueous where it will like go something like
Yeah, so aqueous, it's a little bit more complicated in aqueous solutions, because in aqueous solutions, the volume of the system doesn't really change a lot because of the state of matter, so it makes it that it doesn't change the pressure of the system a lot. In gas phase reactions, you know, if you have more moles of gas on one side compared to the other side, that'll change the pressure of the system. So the pressure affects the system a lot. Yeah, in a chemical equation. Yeah, you can still have molecules interacting each other in the gas phase, and they react with each other, but the total pressure of the system is independent of that reaction happening. All that matters is what's the pressure of each reactant and what's the pressure of each product, and you add them all up, and that gives you the total pressure inside the container. But yeah, so this is called Dalton's law of partial pressure. Right, so if you had, for example, 2 gas canisters, 1 helium at 2 atmospheres, right, that means there's a certain number mole of helium atoms present, another canister with 4 atmospheres of argon present, right? If you mix those 2 together, you just treat each one separately, and that gives you the total pressure inside the gas container. Right? This is an inert system, so those won't react with each other at all. But these gas molecules, since they're so far apart, they don't interact with each other. They don't, you know, attract or repel each other. Right? So the total pressure, having the helium still only sees itself in the container, right? It doesn't even interact with other molecules or other helium atoms. The argon is only associated with the number of moles of argon in the container. So the total pressure is just the sum, is related to the pressure to the sum of all the moles of gas in the system. Okay, and then the last example is just adding the 2 pressures together, so we don't have to go over that. All right, so that concludes all lectures for Chem 60. So now, yay, we're all done with Chem 60. Yay! You guys all made it through your lab checkout. Everyone got their labs all of course, no problem. So right now we have worksheets for gases and acids and bases, since that's the most recent thing that we've done. And then also the practice final has been posted. So let's probably spend time on Monday going over the practice final. Today you can start looking at the worksheets for the remaining lab period, and we can start going over those together as well.